A warm welcome to everybody. And I hope the semester started the best possible way. Can everybody hear me well in the back? Also you guys online? So as I wrote in the email, I mean, lectures are being recorded. So in case you cannot be here, because we often have people who have full-time jobs and they cannot be here physically. In case you're hindered, you can always join online, the Zoom session. Or if not, it's a great pleasure seeing so many faces, okay? I don't mind that. So I wanted just to give you, the first hour today, because there are several practicalities I wanted to discuss with you. So is my English okay? Because I'm not a native English speaker, so I do have an accent. And my English tends to be very much Latinized, unfortunately. That's because I grew up in a country where Latin was the base for the language. So, but hopefully, if something is unclear, let me know, right? So I wanted to start here because this is the official website. So this is the first thing you probably have looked at. And if you have not done so, this is a standard setup. And when you click on the autumn, this is basically where you find the official links. So you will find the schedule. And actually, sometimes when I've been asking for this for many, many years, but nothing has happened. So the schedule comes up in Norwegian. But then if you click down here, you will see there's something in English, which I have added. And then you will find messages. So I should also say that I am this guy with this, for Norwegians, pretty funny name. And these are the other people. These are the TAs you will meet during the semester. So who has not seen this page before? Good. Now, one thing, for those of you who have not studied here before, if you look at this, this is the weekly schedule. And the kind of information which you will get through an email is also something you will actually find information in many, many channels. So you will typically find a link to the lecture notes, etc. Here. You can subscribe to this activity. And this is something which I recommend because in case there are changes, you will get a notification about that. Are you familiar with that option which you have? So you can actually subscribe to the weekly schedule and then get immediately a note in case there are changes. That's just a technicality. So let's go back. And what you will also find is the kind of messages which I'm sending to you by mail. These are also displayed here, but you will also find them under Canvas. So we are going to use Canvas to hand in projects. We are not going to use a software called Insperia. The reason for that is that Canvas gives us much more flexibility with tweaking deadlines. And there's much more to the picture than meets the eye, actually. So we are going to use Canvas as a means of communication with you guys. So the material I wanted to guide you through is actually where you have all the teaching material. So who has never used the version control like Git and repositories like GitHub, GitLab? Anyone who's never used that? Okay, we will actually give you a crash course at the lab. Now, all the teaching material is something which if you click on this address here, and this is the one I wanted to guide you a little bit through first, because this is where you find all the goodies here. This is actually a combined teaching material for two courses, one advanced and this one. If you click on doc here, you will find one weekly material. This is where you find the slides, which I'm going to discuss during the lectures, and the weekly exercises. So this week, when we start with exercises on Wednesday, these exercises are not exercises you need to hand in. I will come back to that a little bit later. So if you click on weekly material and you go to week 34, you will find the Jupyter notebook, and you will find the PDF and the exercises, which we will discuss at the lab session this Wednesday. So this is where you find everything. And if you're familiar with GitHub or GitLab or any of these repositories, you can download all the material and use it as you want. Okay? Any questions? So this is the weekly material. And you will find that one in the emails, which I send during the weekend, so that you know what we are going to do. And you will also find it in the weekly schedule. So there will be many places where you will get access to the same information. So I hope that's not too confusing. Now, I use normally a whiteboard instead of the blackboard. So that means that all the lecture notes where I don't use slides, they will be uploaded later as a PDF. So in case you missed something or you didn't have time to write it down, you can always look up my ugly handwriting. Okay, now the other thing which you have access to is the book. So this is something like 500 plus pages. And this is the textbook which I'm going to refer to when it comes to weekly readings and the material which is relevant for you guys when we're going to solve exercises and projects. Now, the folder here has also a folder with the programs. So every chapter comes with the Python programs. Now, if you don't like them, you can always go back. And if you go to the folder, because I provide, in addition to a standard PDF, there's a Jupyter notebook. No, sorry, a Jupyter book. Are you familiar with Jupyter books? So this is actually pretty nice when you want to search through the whole text. But it contains also the Jupyter notebooks for every single chapter. So you can download them and use them as you want. You can change them, you can adopt them and use them as your own notes. So many people actually take these notes and keep working on them, add their own things. They think that, oh, Morten did an error here, or I don't like this derivation, or I would like to add more material. So use them as your own stuff, okay? So if you just scroll down here, you will then find the different notebooks, chapter 1, 2, 3, etc., etc. And these are basically the chapters which we are going to discuss. So this week, if we go back to the, let's say the PDF, I can just show you that one so you just can see from the content. There are some things which we are going to do here. And one, we are not going to repeat everything in linear algebra, but what I've placed in chapter 1, so don't be intimidated by all the material, because we are going to pick things when we need them. So in chapter 1, you will find the linear algebra, which is relevant for machine learning, the different algorithms. And I will pick now and then from this chapter, and I will point to the different sections and say, this is relevant for these and these exercises. Like next week, we are going to have exercises where you're going to look at derivatives of vectors and matrices. And this is given by this material here, for instance. So this week, the topic which we are going to start with, and we will come back to that a little bit later, is actually regression problems. And it's going to be linear regression. And most of you have probably encountered something which is called ordinary least squares. Does that ring a bell back from linear algebra? So you may ask, where's the machine learning here, right? Because in practice, this is just a matrix inversion. So we're actually teaching, it's normally used as a machine learning method, as an introductory method, because you have analytical answers for many things, which you don't have if you do a deep learning method. Then it's also something which we can solve easily. It's intuitive, and it has a nice connection with statistical analysis. So we can actually catch many birds with just one stone. Actually, that English saying is something which is a little bit more violent, to catch birds with a stone. I prefer the Italian one, which is actually to catch 2 pigeons with a beam, which is much more peaceful. But okay, that's a digression. Okay, and you will find so where we are going to stay this week is essentially in 3.1 to 3.6, and we are going to jump into 3.8 and 3.9. This is the material we will cover this week. Okay, any questions? So this website is the one which you then can, if you just go in up here, you can then just download it on your laptops and use the material as you want. Okay. Now, there is something I have to say first. And probably many of you have been intimidated by AI detectors, cheating, blah, 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 and so on. And how should I use these different tools? So how many of you, I should rather say, who is not using any large language model? Okay. So we actually, in this course, we encourage you to use that. So in a certain sense, this course is a little bit different from many other courses you followed at university, because this is a field which is overpopulated with solutions to all possible problems. So it makes it quite difficult for us to make exercises, okay? Because, I mean, if you just use Claude or you use Gemini or ChatGPT, you can actually get pretty nice programs which solve most of the problems we have. So that means that when we are making the exercises and the projects, we are going to dive a little bit deeper, and we're going to trigger your insights about the science which we're doing. So that means that in the grading of the projects, etc., there's going to be much more emphasis on that. I also have a file here, and I want you to look at that one. And this is tentative yet, but actually a little bit about the guidelines on how to use them. So as I said, this is a field which is overpopulated with lecture notes, solutions, etc., etc. So that means that we are also going to show you how you can use these tools efficiently. So during the lab sessions, we're going to show you how you can set up skill files with Claude and then govern a large project. Has any one of you used that? So Claude comes, is anyone using Claude as a large language model? Okay, I'm not paid by Anthropic, but to me, it's actually the best one when it comes to programming. And we are going to show you examples in the lab sessions on how you can use these tools in an efficient way. Okay, yeah?
But are we like expected to use them or?
No, I mean, this is a tool which is there. So you can, so like I belong to the people who do the hard coding myself, and I like it like that. But if many of the codes which you are going to develop, many of them actually contain elements from libraries. So you would actually have to put together elements from, let's say, a library on calculating the inverse of a matrix. So in this course, you're not going to write a program for inverting a matrix, but you're going to use numerical Python to do that. Or at the bottom of numerical Python, there's a library which is called LAPAC. So there are many elements which enter here, which are already ready for you. So assembling them is something you can do yourself, and I normally do that myself. And then you can use these tools, but it's not something which we require. But since many people use these tools, then we have some rules which we would like you to follow. So that means that when you write the projects, we actually have a kind of expectation of what you declare. Okay? So this is something which many of you will probably still struggle with and be in doubt with about how should I use them, how should I declare them properly. And that's the kind of discussions we will have at the lab. But when you deal with machine learning, so just to give you an example, if you look at all the programs which I have in the website here, so what I did this summer was actually to take all programs which I have written in C++, actually have lots of dusty old Fortran decks in Python, etc., and I've synchronized them using Claude. That saved me a lot of time. So the thing is that I have been coding for 30, 40 years, so you have this kind of insight. What we want to give you is the insight behind the algorithms, so that you know how to use these methods in a critical way, because that's where we want to end. We want you to be critical citizens and critical users of these softwares. There's probably much more, but we will come back to that during different lab sessions. So this is something which we want you to have in every project. Another thing I wanted to show you before we move on is the project link. And there is one on evaluation and grading. So in this course, there are no exams. I mean, there's only 3 projects. So this is actually what counts to the final grade, plus the weekly exercises which you hand in, which give an additional score. So if you look at the evaluation and grading, these are the rules of the game, which we are going to follow throughout the semester. And you will find examples of reports here, so you can look at those, but also we encourage you to discuss with us at the lab. So the lab is the central part of this course. The lectures on Mondays, like this one, they serve often they will actually be like traditional lectures, where I will try to set up the plan for the week and go through the basic elements. Then Tuesdays, we will be upstairs, and we will use that more as an active learning environment, in the sense that I will go through questions and have a mini lecture the first 20, 30 minutes. And then we are going to look at exercises, work on exercises, and have questions and back and forth. So that's more an active learning environment. However, this Tuesday, in order to get up to speed, I'm going to have a kind of almost regular lecture. But the Monday serves as the entry point for the week and defines what we do this week. And the Monday lectures are always recorded. So if you look at the evaluation grading, there is a file here where we now look at, so we want you to write the projects as scientific reports. And there's a reason for that. One of the reasons is that many of you have probably not written a scientific report like a scientific article. This is something which you will end up doing. The basic format here is essentially the same way you will write your master thesis. You will write a technical report in a company, or you will write a scientific article. So the elements which you see here are those which we want you to follow. And that file contains essentially a guideline. And you will also see that the kind of points which we give here actually now have a large focus on the analysis. And the reason for that is that in the analysis part, that is where we can see what kind of insights you have gained through the project. Because technicalities, what we saw last year and the year before, is that many people actually wrote perfect codes. And it's very difficult for us to say whether this was done by you or by somebody else. So we have tuned down the coding grade from 20 to 10, as you can see here. There's also something else which we have done, because these are take-home projects, is that the grading scale is pretty narrow. So you need a score of 60 for a pass. Normally, if you do a regular written exam, the no pass score is typically 40%. But since these are projects which you will work on for a month, there's plenty of time to actually perfect them. There's another thing which we also do. Not this week, although there is an exercise this week, but next week and on, we will have exercises. You don't need to do them, but these exercises align with what we will do in the projects. So if you do them gradually, when you're getting close to the deadline of the project, you basically have a lot of the programming elements which are needed for the project. One reason why we did this is that we had always 30% of the people who are like me, horrible procrastinators. I mean, we start working on a topic one day before the deadline. And then, you know, this is a recipe for total panic. So by doing these exercises week by week, you will have the elements which are needed for solving that specific project. And you get an additional score. So for every weekly exercise you hand in, you get 1 point. Now, these exercises are not graded. So the feedback you get is, well done, keep up the good work. And if we see something wrong, we will obviously flag that, but you will not get a detailed feedback. Also because the TAs are students like you, and they're also following courses and also have other things they want to do. Then you can then see that if you suppose you have only 3 projects, you have 88, which would be a B, but you've done 7 of the weekly exercises, then you have 95. And then that turns into an A. So as I said, these weekly exercises are not graded. There's a minimal feedback, but the projects, we typically give you, we hope to give you a decent feedback. Okay, any questions, guys? Everything crystal clear? So I'm going to repeat some of these messages. And some of you will probably be offended. It's like my daughter always kicks back and says, Dad, you said it once, you don't need to repeat it twice. This is what you call a professional distortion, right? In the sense that as a teacher, repetitions are important. But I know that there are many small things here, and I will repeat some of them tomorrow and perhaps next week as well. And if you get bored by me repeating too much, just flag and just tell me, hey, Morten, stop now. We've got the message. Okay. So these are, and then there are some basic general guidelines on how to write a report. So take a look at this. There's a lot of material here. I hope you will enjoy it. I've enjoyed writing all this stuff. And as I said, the textbook is the one I will refer to. And then what I want to do now is actually to dive into some more practicalities. And I wanted to actually look at the slides for this week. So this is this week's material because it contains some more information. And we will go through that one before we begin looking at the theory itself for linear regression. So as you said, the lectures on Mondays and also Tuesdays will be available via Zoom. I will also place videos and things like that on specific material. This week, we are going to start with linear regression with examples and discuss some of the basic elements. And then at the lab, we are going to look at this, some basic elements of programming. Some of you may have forgotten about different libraries, etc. So there are lots of small practicalities which we typically deal with the first week. You can also hand in these weekly exercises, but you will not get a score for week 34 because this is more seen as a warm-up. So these are things which you probably have seen. So we have weekly reading assignments and videos will be communicated to you. The lab sessions typically last 4 hours. We have notes, etc. They are at the homepage. You can just download that one. For communication, I tended to use many channels, but now we just decided to reduce that to Canvas. And through email, you can also use the chat function in Canvas. If you guys want to, you can set up channels in Reddit or whatever and have discussion channels among yourself. Many people do that every year. So as I said, there are 3 compulsory projects. The evaluation and grading, so they're graded and each counts 1/3. There's no final or written exam. I should also say that in case we had only, I'd say every year we had 1, 2, 3 cases of people where we were in doubt whether that person had actually done everything herself or himself. And then we will always ask you in person, what did you do here actually? So just to give you an example, in one of the cases which we were in doubt, the program was perfect, but the analysis, the text had no connections with the figures which were presented in the text. So it was a pretty obvious case that something had just been filled in automatically. So what we typically do then is that we would just contact that specific person and ask, hey, what did you do here? What did you mean here? So we will not use any of these kind of, as many people threaten with AI detectors. So that's out of question. So we trust you guys, and we trust that what you are after is actually a deeper insight about the problems. Okay. So you can reach me whenever you want. I try to answer as quickly as possible. So let me just say one thing. This plan is tentative. So that means that if some of you or a fraction of you have problems with that date because there may be an excursion or something else, we can always change the dates. But these dates are for your planning. So we are planning to have the deadline for the first project in the beginning of October, and then the next one in the beginning of November, and then the final one around December the 7th. So we always tweak these dates because sometimes something happens, etc., etc. Okay? So if you see some problems now, please shoot us an email. I'm going to skip this one, but I wanted to say something about the textbooks. So there are two main textbooks, which I also will refer to in the lecture notes and during the weekly mails which I'm sending. So one is the textbook by Goodfellow, Benjo, and Colville. Benjo, probably somebody of you have listened to him last year. This is the really one of the big inventors in machine learning and artificial intelligence. And they have a textbook where you can access every chapter. So everything is fully accessible. So it's an online textbook, and you can't download them and print them. They have hindered that because there's some copyright regulations. Then there is another textbook by Sebastian Raschka et al., which it's pretty similar to my own in philosophy, but it contains less mathematics. So in this course, we actually point more to the mathematics behind the algorithms. So this is something which we want you to look at. And this textbook by Raschka, this is something you can access through the university library. So if you go to the university library, have you done that before? So who has never used the university library? Okay, so the university library system, let me show you that one so that we can uncover that one. So you have something which is called aurea.no. And now you get to the University Library, University of Oslo. And then you will typically punch in an author or whatever. And then you will get a flag which says whether this is available online or not. So the university actually pays a fortune to many of these big publishers so that you have free access to the books, articles, and so on. So the book by Raschka is fully available for free, for download. And I will refer to different chapters when we move on during the semester. So these are the two books, plus my own lecture notes, which we are going to use as teaching material. So let me just go back here to this about popularity. These are also some other popular texts. And you can see here now that the kind of stuff which I recommend looking at is to refresh linear algebra. And in GBG, that is Goodfellow, Benjo, and Colville, chapter 2. And in my book, it's chapter 1. And then linear regression, chapter 3. So I'm going to skip some of these things here. You can actually look them up. But I wanted to say a little bit about the machine learning methods, which we are going to cover here. So we start with linear regression, although this is something which was invented close to 200 years ago by Gauss and other people. And there's actually a long story behind also the Gaussian distribution. Do you know the legend about the Gaussian distribution? Now, the University of Göttingen had actually, they were facing a problem because many of these old professors, they tended to marry younger women. This was pretty common. And the university was worried that they would have pension obligations to people who would live much longer than these old farts. So what Gauss did then was actually to look at the age distribution. And that's how we come across the Gaussian distribution. And then he could, calm the university leadership and look, the Gaussian distribution tells you the probability of how long people will live. So the university felt reassured that they would not go bankruptcy due to pension obligations. That's a small legend. I don't know if it's true, but it's a fun story. And Gauss, this is one of the intimidating things. Gauss appears everywhere. Gaussian elimination, Gaussian distributions, you have Gaussian iterations, etc., etc. So you will see in the linear algebra chapter that there's a lot of reference to Gauss. So linear regression is important. It's important because we have many analytical results. I'm going to repeat some of these things later. We are going to also link this with a little bit statistics. And then we have some methods where we will be a little bit more sloppy and put less emphasis on. And one of these is support vector machines. But we will say something about decision trees, which is a very intuitive method. And but then the main focus, like in project 2, is going to be on deep learning methods. So you're actually going to write a neural network code from scratch. This is one of the things we want you to do in project 2. And we're also going to cover methods like convolutional neural networks, recurrent autoencoders. Generative methods is something which is in the textbook, but it's covered in another course. But if you want to look at it, feel free to do that. Then there's a list of tools, which I will not go through now. And then there's a link to other courses if you're interested. And if you find something which is missing, there's actually at Department for Computer Science in Informatik, they have established a new course on agentic AI. This is actually the course I would have liked to teach. But that's a new course, and I don't remember the code here. Now, learning outcomes, this is something I want you just to look at, because right now they often don't say much. And this is something which I always come back to the end of the semester. But take a look at it now. And then when we move on during the semester, you can see whether we have reached these learning goals or not. So I'm not going to put an emphasis on now. So there's a lot of text here. But I wanted to say something about the types of machine learning which we're dealing with. So I'm not reading every word here because you have access to the information. But essentially, 3 types, main types of machine learning tasks. This is the first thing. And one of these is classification. So you can have an algorithm which trains on paintings of Munch and learns to distinguish a Munch painting from a Van Gogh. So that would be a classification problem of the simplest type. That's a binary classification. Yes, no, 1, 0, true, false. Is it a Munch or not? So that's a typical problem which we're going to look at and arises in many, many scientific applications, obviously. If you're dealing with applications of machine learning to medicine, I mean, you would like to classify whether this kind of pattern can lead to heart disease or not, etc., etc. Then we have regression, which is where I am basically in, and that's about finding a functional relationship between an input data and a reference data set, and then we fit a continuous function. So that's the one of the other typical problems which we often end up with. Then we have clustering, which is more when you have data where you don't have a specific label. So this classification and regression problems are typical data sets where we have labeled the data. but you often end up in situations where you have unlabeled data. So labeling the data is actually expensive because often there is a human who has labeled whether that is true or not. And so these are the type of problems which we are going to deal with. I actually forgot something. No, yeah, and we are mainly going to deal with, since I said labeling and not labeling, with the supervised learning. Supervised learning means that we have data which is labeled. Unsupervised means that we have data which is not labeled. And that is often the interesting case because you can have trillions of data which you want to, let's say, classify according to some specific rules which you have devised. And when it's not labeled, you have to figure out other methods. So we will, in the methods which you see up here, we will, to a large extent, stay with the labeled data. Autoencoders is one of the first encounters where we have can have unlabeled data. For generative methods, this is more the standard situation. So let me just scroll down and try to point out some other things here. So the three basic elements, and I'm coming back to that when we now start with linear regression. So these three basic elements are, one, the data set, which we have access to. Then we are going to make a model, which is going to describe the data. So it's actually us who makes a model about the data. And that insight we use reflects our insight about the scientific problem. Then finally, we need to define a function which assesses whether this model is doing well or not on the data. So these three steps are essentially the three steps in a machine learning approach. Now, since you are going to introduce parameters, that means that the so-called cost function which we have is a function which depends on the parameters and which we are going to optimize. So at the center of all machine learning, there is an optimization problem, and that's a bottleneck. And you will see then in the different chapters, there's actually a dedicated chapter 4 on optimization. And project 1 is going to deal with us implementing some of these optimization algorithms on linear regression. That's the essence of the first chapter, just to get a feeling of what the optimization actually means. And then there is something in the optimization which makes life sweet. Have you heard about automatic differentiation? Has anyone heard of that? Only one of you. Another one. Good. And another one. Okay. Don't be timid, guys. Eh? Yeah? Yes.
So is it just differentiation or is it the use of special quantities that are automatically?
Now, automatic differentiation is a mathematical algorithm which allows you to calculate derivatives to numerical precision by repeated usage of the chain rule. So it's a hidden gem in numerical mathematics, but it is the one which saves the day because you're going to have functions which depend on zillions of parameters. And you're going to calculate gradients in the optimization part. And when you change the functions which you have as a trial functions, you don't want to sit down and write the analytical derivatives or calculate these by hand. This doesn't give you any new insight. And that's where automatic differentiation comes in and saves the day. You're probably used to something called finite differences. These are the standard formula. You have the finite difference formula, which leads, for instance, to Euler's algorithm or some of the standard ways of calculating a second derivative. These actually don't give you precise values, especially when you tune down the step of the step length. Any questions? So automatic differentiation is going to be an important tool. And there is a library which is called the JAX, which also stands for just-in-time compilation. And it includes automatic differentiation. And you will see that that is a tool which is going to make life much, much simpler when you write codes. There are many hidden gems in linear algebra, which we tend to forget about. So what I wanted to do, I'm not going to say everything here, but I wanted to say a little bit about some of the methods which we end up with dealing. So before we take a small break, and then after the break, we are going to dive into our first derivations of linear regression. But I wanted to say a little bit about some of these methods which we end up dealing with. So discriminative methods are central methods in machine learning. So what does discriminative mean? So you can understand it from this approach here, where you take, in this case, Van Gogh paintings, and you want to train a model. This model then discriminates between whether this is a Van Gogh painting or not. So many of the methods which we are going to look at belong to the discriminative class. A neural network belongs also to that class, but a neural network can also be used to solve differential equations. And then it becomes a generative method. But a generative method is actually a little bit more than just being able to solve a differential equation, because a generative method is a little bit more interesting. And this is what enters actually many of the large language models. If you have used a drawing tool like DALL-E, is that a software which you're maybe familiar with to make images? So they are based on or if you use ChatGPT and ask ChatGPT to draw an image, they use basically generative methods. So what does that mean? So it means that you will train on, let's say, images of horses, and you produce not a model which is very deterministic, but you produce a probability distribution. That probability distribution, which is much more interesting when you do science, because if you have a standard discriminative model, you can make a prediction, which is what you want to do. You can find correlations in the data, but when you have defined a probability distribution, like a Gaussian, then you can, make predictions, you can find correlations, you can calculate something which in statistics is called the covariance function, but you can also study causality. What is the probability of A given B, since you have a probability? And you can also estimate the errors, which you cannot do in what is normally called a frequentist approach. So how many of you, and this is actually a little bit delicate thing, because we have failed a little bit in many of the bachelor programs throughout Europe. This actually applies to many countries, and that we don't have a proper training in statistics. So when I say something like a frequentist approach, does that ring a bell among you guys? Okay. If I say Bayesian statistics, does that say something? Okay, there's a good fraction of people. So these are concepts which are going to be there under the hood and which we will bring up now and then. Chapter 2 of my lecture notes contains a description of these different approaches. But this is just a rough distinction between the type of models which we will deal with. We will mainly stay with discriminative models. We will deal with supervised learning, but we will also touch upon unsupervised learning. So that's basically what we will do in this course. I hope that was not disappointing. So there's much more here actually, and I invite you to take a look at it and take a look and read at it. So after the break, I'm just going to scroll down a little bit. There's a lot of software and so on, which we are going to discuss, but I wanted to go back to some of this material. But after the break, we are going to look into the mathematics of linear regression. And there are several arguments here why you will typically find this in a textbook on machine learning. So in general, you would think that this is not. What does this have to do with machine learning? The machine learning here comes in because you learn the parameters which optimize the function you want to optimize. So you have an algorithm to learn the parameters, the unknown parameters. Now it's a deterministic algorithm. It can be solved by simple matrix inversion. but it has a lot of nice connections. As I say here, you have analytical expression for statistical properties. You have analytical relation with probabilistic interpretations. It's easy to introduce many of the concepts which you will meet later. And it also allows us in project 1, when we are going to discuss optimization methods and so-called gradient methods, this allows us to have a solution which is analytical and a function whose properties we know exactly what they are. So if we then don't get back the exact result, we have done something wrong in project 1. So when we are building up this machine learning says a library, which you will do in this semester, and end up with deep learning methods like neural networks or recurrent neural networks, then the basis is something which we can bake in a pedagogical step-by-step approach by starting with linear regression. So you will, I mean, many people get surprised, but you can think of linear regression as a low-level machine learning method. That's the way I like to think of it. And then for classification, we have logistic regression, which is a similar method. But in that case, we don't have analytical solutions anymore because the equations are no longer linear. So when your equations are linear in the unknown coefficients, often we can find analytical solutions. So keep that in mind when we meet after the break. Now, I should stop here now. Feel free to stretch legs, ask questions. Don't be shy. I mean, I always welcome questions. I had a teacher who said that he didn't take questions during the break. I was very disappointed. Okay, guys, let's take a small break, 15 minutes. Is that okay? So welcome back. And before we now dive into linear regression, there is a message which I forgot to give before the break. And when it comes to the projects, we normally encourage people to work together. So typical groups, 2 to 3 people, tend to be optimal from experience, but we had groups of 4 to 5 people. So some of you may know somebody, you have studied together for many, many years. Some of you are not from here. So what I'm going to do, I'm going to send you a link to a Google Docs where I want you to list your background, and then I will try to team up people according to the background. So what I often try to do is to team up people, perhaps from the same study program, or if somebody's an expert in mathematics, with somebody who's good at computing. And then the third person could be somebody like me, who is good at making coffee and cracking lame jokes. So you need somebody like that as well. But I'm going to send you this link so you can just fill in case you don't know somebody and you would like to team up. So as I said, we've also had groups of 4 to 5 people, but that means that you need to know each other pretty well. I should also say that the last project is actually a project where we are going to make suggestions, but it's a project where you can come with proposals. So, and some of these have actually ended up in scientific publications. We had a group once with an expert in geoscience who had the drill data from Equinor. And there was another participant from informatics who was an expert in transforming the data into the machine learning format which was needed. Actually, this is something which we will not discuss that much in this course, how to transform data. We are going to do some basic things, but we will not put an emphasis on that. And that can quickly become 70, 80% of the job. So most of the cases we are going to look at, we have well-defined data sets, which we can plug in a given machine learning algorithm. But that group had then also somebody who was expert in mathematics. And there was a final person who was very good in all these things. So that group worked really well with different types of expertise. And one learns much more by collaborating. The other thing is that the projects, you will probably see that when you see the project coming up. We want you to hand in either PDF which is a normal format, but we also want to have access to the GitHub or GitLab or repository which you're using. So that's important because then we can test codes, etc. These are things which we will discuss at the lab. So we will give you the instructions on how these submissions should be done. And submissions will be done via Canvas. Yeah. Yeah. So we've had groups where you hand in one report. So everybody gets the same grade or score. Or we had groups where people collaborated. They stated that they've been collaborating, but they wrote each one wrote their own report. So this is very much up to you guys. So we want you to have this kind of flexibility. But the easiest one is just to hand in one project per group. And that makes it easier for us when we grade as well. Yeah.
The exercises are those also in groups? Or?
So you can do you can hand in as a group for the weekly exercises, or you can hand in individually. So this is up to you. So if you are a group and you collaborate on the weekly exercises, it's pretty natural that you would hand in just one weekly exercise. Yeah. I just need to take off this because my hearing. No.
So it's up to
No, there's nothing. In this course, the only mandatory things are the 3 projects. So you can choose your working models as you want. I mean, we encourage you to collaborate because it makes life easier. And when you have software like Overleaf, are you guys using Overleaf? Have you used that one for writing reports? That has version control as well. So many people can edit on the same file. And that makes life much, much easier. So these are things which we also will discuss in the lab sessions. Which tool are those which are, how to say, handy when we do science? More questions? Okay, so what I want to do now is to switch over to my whiteboard. So what you see here is just a list of the whys you will encounter linear regression as one of the first machine learning methods. And as I said, I like to call this a low-level machine learning. And you're going to see now from the mathematics that what you end up with is a simple algorithm to find the unknown parameters. So let's switch to the whiteboard and slow down the pace a little bit. So can you see well? Okay. So I said that there are actually 3 basic ingredients. One is the data, the other is the model, and then we have a function to estimate whether this model is okay or not. So what we want to do is typically to reproduce some kind of data with some model which we make up. So let me just bring in some basic definitions first. So we are going to define an input, and we define an input vector, which now contains our data. So this is a vector when you see it like this. And then this is going to be the transpose. So these are input points, x1, x2, up to some xn minus 1. And this is transformed like that. So this is the input. So this could be, suppose now that you measure the position of a car. Or rather, since I don't like cars, a bike. I'm a cyclist. And I think cars, yeah, I shouldn't say anything more about that. Okay, but suppose this is a cyclist and you measure the position and you want to, as a function of time, and x could be time, and you have the position. And then you want to make a model for that. So this is your input, so it's pretty simple, and you measure time at given steps. And then we have a vector y, which we now call the output. So we are simply going to use these two names here, inputs and outputs. So this is our data. And in this case, we have some observations, and we just call them Y0, Y1, Y2, up to some yn minus 1, and it's transpose. And both x and y, we assume them to be real numbers. There could be other types of numbers, and they have length n, like this. So this is our data set. This is the input. So we can set this up as number 1 here. That's the first element which we have. The next one is that we have to make a model. And this is where you have to bake in your insight about the problem. So the second stage is the model stage. So making a model. So that means that in our case, we are going to look after some function, which now is going to approximate y as a function of x. So y is the data, the output, which is a function of the input. And we are going to make an approximation here where we have some function which is going to depend on x, but it's also going to depend on a parameter set theta. So these are parameters. And I'm going to assume that this is also a vector. It doesn't need to be a vector. Now we are just making vectors of the inputs and the outputs, but they could be matrices, or they could be tensors, higher order matrices. So theta here would be some theta 0. So these are the unknown parameters, which we are now plugging into the model here. And now we let this go to p minus 1. And this is transposed. So why do I begin with 0 instead of 1? Yeah. Say again. So if you program in languages like Python and C++, the array starts with element 0. If you do Fortran, it starts with 1. Just keep that in mind. So this is something which is always a pitfall when it comes to memory problems. So I'm just trying to keep the notation here as close as possible to the way we would end up programming. Now, suppose now that we have this cyclist whose position you measure as a function of time. If you now didn't have any insight about Newton's law, what would you suggest as a function to fit the output as a function of the input? Any good suggestion? What's the simplest possible function you could think of to fit? Any good suggestions? Yeah? Say it again. Yeah, a linear function. Or you could make a high order polynomial, right? So what we could do now is simply to define this function f. This is our model. So we could say now that, suppose now that f of x, and now I'm putting in x of I, as a function of these parameters theta, is given by a polynomial. So a linear function is obviously the simplest polynomial, but I could set this up now as a function which is given in terms of a polynomial of a specific degree, j equals 0, up to some number m minus 1. And then I have some parameters. I have my x of I. And this x of I is now to the power of j. And it's multiplied with this parameter theta of j. So this is the compact version where I now have defined a polynomial of degree n. And if we take the linear model, then if we do that, if we make this linear, then this f of x of I of theta would just be given by theta 0 plus theta 1 multiplied with xi to the power of 1. I hope you don't get offended if I start with such a simple case. But this is the model which we could make. And in some cases, the signs which you're dealing with can be actually pretty well reproduced by a polynomial of a certain degree. And I should say the following. If a polynomial does a job for you, there is no need to introduce a neural network, which is a much more complicated algorithm. If the polynomial is the one which fits the data best, you stay with that. Okay? So it sounds a little bit disappointing because, I mean, this is a course on machine learning, right? And you have this guy who says, if a polynomial does a job, why should I bother about the other methods? We will try to see why. But if a polynomial does a job, then this is what we would have as a model. Now, let's try to write this in a more compact way. So what we're going to do now is to write it more as a matrix times a vector, using some matrix vector notation. But if you now look at, suppose we now assume that we make a specific model. I need to look at my cheat sheet here a little bit. What we can do, suppose we have a polynomial of degree n minus 1. So we have n data points. So that means that if I look at my y0, the first point, that is going to be given by theta 0 plus theta 1 times x0 to the power of 1 plus theta 2 times x0 to the power of 2. And this goes up all the way up to x0 to the power of n minus 1 times theta n minus 1. So this is just one of the points of the output, y0. And then if we just move on here, we have y1, which would obviously be given by theta 0 plus theta 1. So these are the same for every input and output, the thetas. And then we would have x1 to the power of 1 plus theta 2 times x1 to the power of 2. And this just goes on all the way to x1 to the power of n minus 1 of theta n minus 1. Now I'm just going to put dots in here, and we're going to have yn minus 1 is equal to theta 0 plus theta 1 xn minus 1 to the power of 1. And then I'm getting lazy, but I hope that you see the pattern here, and I don't need to fill in all these, of n minus 1. So this is what we would have to fit or find the optimal. So the thetas are unknown. Now, if you look at, yeah. My hearing is bad, actually. Yes, yes. So so the parameters could be a function of theta. It could be a sine function, it could be a cosine, etc. So you're not limited to this simple polynomial which I'm setting up. But I'm setting up a polynomial because this is something which most of us are pretty familiar with. But as you say, I mean, this could be a series of exponentials, sine functions, whatever, is appropriate for your scientific problem. Now, if you now look at this equation here, so what I've done is, how to say, not very exciting, and it's also not very compact. Is there a way I can compactify this equation here? If you think back in terms of the vectors which I have defined, so we defined these two vectors, and we defined this vector theta, and you see that the vector theta appears theta 0, theta 1, all the elements. If you look at what we have here, can I write this in a more compact form? Is it just to bring back some linear algebra? Yeah? Yes. So I can keep the vector, so the y, which we have on the left, is a vector. The x is a vectors. And, but the way it's put up now, it looks more like a matrix, and theta is a vector. So let's now take a look at how we can rewrite this one. And I have to be a little bit careful with low key letters and upper key letters. So I can rewrite this equation as y, and let me put a vector sign. Because if I boldface it, it's just going to look ugly. So this is the vector y, which is simply every single line which we have here. So this is y0, y1, and all the way down to yn minus 1. And now I want you to make a distinction because this is an uppercase letter x. This is going to be a matrix. And this is multiplied with the vector theta. So which is then given by theta 0, theta 1, and theta n minus 1. So this is going to be a matrix. And when I write it, it's going to be a matrix times the vector theta. And I put a vector sign here just to distinguish vectors and matrices. So if you look back now, you will see that every element which you have here, x, this will be 1, then x0 to the power of 1, x0 to the power of 2, etc. These are the elements of that matrix X. So let's just put that up. So this matrix X is then simply going to have, for theta 0, there will just be ones, 1, 1, all the way down. And then I have x0 to the power of 1, x0 to the power of 2, and x0 to the power of n minus 1. And then I have x1 to the power of 1, x1 to the power of 2, and x1 to the power of n minus 1. And this goes all the way down to xn minus 1 to the power of 1, to xn minus n to the power of n minus 1. Now, in linear algebra, this matrix has actually a name after a mathematician. Has anyone encountered this matrix when you now take all the points you have available and you're making a matrix which is now symmetric, not symmetric, but quadratic? Yeah?
Van der something.
Van der Monde matrix. So this is called a Van der Monde matrix. Normally, we will not use a polynomial of degree n minus 1, but we will typically have a smaller polynomial. So if we have a polynomial of degree 2, we will only have 3 columns. So this matrix, which you see here, has a special name. And this is what in machine learning is called the design matrix or the feature matrix. So you can think of every column here as a specific feature. So think of a polynomial now. So the feature is the degree of the polynomial. So the second column represents numbers to the power of 1. The third column, numbers to the power of 2, etc., etc. Okay? So this is the famous design matrix. Design or feature matrix. And this is a central object in essentially all of machine learning. So this is a typical way we would now encode the data in our model. If you're dealing with neural networks, the network is actually going to find the features for you. And then you would just encode X, because else you would force the network to produce a polynomial of a specific degree, which may not reflect data you have. So if you now set a polynomial, we are going to change notation a little bit. So we are going to define a polynomial. This is a more general case, a polynomial. It doesn't need to be a polynomial of degree p minus 1. That means that the function which we are trying to approximate, this f of x of y of theta, is now simply going to be, in our case, a polynomial approximation, which goes from j equals 0 up to p minus 1. And then we have the x of I to the power of j multiplied with theta of j. So that means that the theta is now a vector of length p. We have x is a vector of length n, and y is a vector of length n. I'm going to have to put arrows here in order to distinguish that from the matrix X. So the matrix X is, on the other hand, in general, a matrix of dimension n times p. So it doesn't need to be quadratic. And this is a norm. So if I make a second order polynomial, you could then think of all these i's, xi's, as specific measurements you make of, let's say, time. And then your output is a position of somebody. And then you want to make a model. And in this case, a linear model is the one which would agree with Newton's law. But you can make it more complicated. So if you have a second order polynomial, let me just write it down. Is okay? Can I change page? Is everybody fine? So if I have a second order, if P is now equal to 2 here, sorry, actually it's P is equal to 3. I was wrong here. Then what I would have is that f of x of I, an individual one, is then given by theta 0 plus theta 1 times x of I plus theta 2 times x of I squared. So that's a second order polynomial. And our matrix X would then simply be have 1s here. And then I would have x0 to the power of 1, x0 to the power of 2. And this goes all the way down to xn minus 1 to the power of 1, and xn minus 1 to the power of 2. And X then would be a matrix of dimension n times 3. Okay? Now, each column represents a feature. So if you look at the column here, suppose we now single out this specific column. That is a specific feature. Or property. So it's often also called, you will find this matrix to have different names in the literature, but we will typically use feature or design matrix. It's a design of the model you made. Sometimes it's called property matrix. You could think of replacing these columns with housing prices and properties of a house. So perhaps you want to make a model for the price of a house, where the properties are the number of rooms, the size of the house, the number of the floors, etc., etc. So these will be the properties, and each one would then represent a column. Now, there are several small technicalities here, which we will also discuss tomorrow, and that clearly deals with how these features are aligned, because many of the features can then represent different properties. Suppose you're making a meteorological model. So one column could represent the pressure, another one could represent wind speed, another one could represent the air temperature. Now, these properties need to be scaled because they have different units and different dimensions. So this leads to a problem called scaling, which we will have to pay attention to, because that will affect the model which we train. So if some parameters go from minus 10 billions to plus 10 billions, and another parameters ranges from 0 to 1, that can easily lead to numerical problems in the fitting. So it's common when we have a data set that we are going to scale the different columns so that they become dimensionless. That is pretty common. And another thing, this is a small digression. So we once had a master student who spent 2 months, wasted 2 months, simply because the data had different units. So the wind speed was measured in kilometer per hour for some years. And then other years, it was measured as meters per second. And unless you looked at the data set, you wouldn't have realized that. So then this person actually went through the data set and saw that, hey, the data are recorded differently from year to year. So these are problems which we can encounter. And that's why if you have the possibility to look at the data set and analyze it and see if it's recorded properly, et cetera, these are important features when you deal with a data set which you haven't handled before. Okay, so now we have defined a model. And if you now look at the model here, the way we wrote it, we actually wrote it like this. So the parameters theta are the unknown. What do we call a model? Like this. Or how do the parameters behave? Are they exponentiated? Are they linear? So how do you call the model of the parameters? Is that a quadratic model in the parameters? Is it a, yeah? This is a linear. And this is why this is called linear regression. So the equations with the unknown parameters are now linear in the unknown parameters. So this is called a linear dependence. Sorry for not expressing the question properly. So it's linear in the unknown. The matrix X doesn't need to be linear. And you see that every component in X represents the degree of the polynomial, a feature of the polynomial, or property of the polynomial. And this is why this is called a feature matrix. So every column represents some specific feature. And you see that immediately if you just go back to the previous slide. When you look at it, this, every column then simply represents a specific feature of the polynomial. Now, you also see, and when you're going to see the final algorithm, where we are going to invert a matrix, the properties of this matrix become crucial. Because now we have a polynomial approximation, which means that basically every column vector will be orthogonal to the other ones. So we cannot have two columns which are just given by each other by just a constant. But in general, this is going to be a huge problem with the data sets which we have. And that will lead to matrices which cannot be inverted. So these are typical problems which arise. But if we have a property like a polynomial approximation, life is going to be gentle and kind to us in general. Okay, so now we did the model. So that's this part. The next step is to assess the model. Let me just bring up that one. And this is assessing the model. And that is whether this is a good model or not. This leads to the introduction of a function which is normally called loss function or cost function. And I'm putting up the names which you will encounter. Alternatively, if you go to finance, it's often called the risk function. And then I put dots here because there are many, many different ways this function is named, depending on the literature. Some people call it the error function. So what I have now is a model. And now I'm going to simplify a little bit my notation. So what I'm going to do now is to define a variable y of I tilde, which is actually given by this function x of I of theta. So that means that I'm going to have a vector y tilde, which now is simply given by all the values which my model gives. And you see that y tilde is also an object which lives in this dimension here. So this is just a shorthand. Now, if I'm going to ask you, suppose now that you have made this model and you have the data, what kind of function would you suggest as a function to measure whether the model is good or not? So let me just write it down here and see if I can trigger your insights. So I want some suggestions for functions which assess if y is a good or bad model. So I'm going to give you a hint here. I'm going to give you one example. So one example which we could think of. So now I'm going to set up this function of y and theta. I call it for a cost function. And I could think of, so one function which comes immediately to my mind is the absolute error. So I could now set up y of I minus y of I tilde. Is this a function you think could be reasonable? Yeah? That's a good point. And would you like to say why? There is another thing here, and which is important for us, because I said that at the heart of all of machine learning, there is an optimization. So what we are going to calculate are the derivatives of that function. So what we want at the end, so let me just write it. So we want the gradients of that function with respect to the parameters theta. And we want this to be 0. So this function is actually a function which people use as a way to assess the quality of the data. So it's fully usable. There's nothing wrong with it. You could also define the relative error, where you would divide by the value y, because the relative error is often more interesting. Now, if I take the derivative of that function, so now we are thinking of a practical way of driving that function to 0. So if you now spool back and go back to perhaps the first semester when you looked at the basic analysis, if I take the derivative of that function, what kind of problem could I face? Yeah? Yeah, exactly. So we have the derivatives of an absolute value, and that gives a jump at 0. Yeah? That's also critical. So we want a practical algorithm. Yeah? Can you say it again? Yeah, that's also a good point. So can everybody hear what people say? So I would probably not repeat for those of you online. I'm sorry for that. Also, I don't think you will properly hear, you cannot properly hear that. So this function is perhaps not the best. It's a viable function. Actually, people often mix different functions when they optimize. But there is one function which we could call the handy one, which gives us nice analytical derivatives. Does anyone remember? Yeah? Yes. Which leads to the mean squared error. So that's one of the functions which we typically use to define such a cost function. And that function is going to lead to analytical derivatives. it's going to lead to an analytical expression for the parameters theta. So the function which we will use here when we derive these equations. So Gauss did the derivation using both the linear algebra concepts, which you will see now. So now we're going to take a linear algebra route. But Gauss did also derive it using the Gaussian distribution, a multivariate Gaussian distribution. And you end up practically with the same function to optimize, the same gradients. So let's look at the function, which is one of the more popular ones. But keep in mind that you can mix different such functions, depending on how your data looks like. So if you have some insight about the data, there could be some data which are best assessed by mean squared error, and other ones which are assessed by the absolute value. So this function here is fully viable. There's nothing wrong with it. But the next one is going to give us an analytical expression for the unknown parameters theta. So the mean squared error is a function which I'm going to define as follows. So y of theta, and I'm going to divide by n, because later I will use this as an expectation value, a sample expectation value. This is a concept from statistics, which we are going to come back to later. You will see often in many textbooks that they skip the 1 over n, or they even have a factor of 2 in front of it, because that takes away, or a factor of a half, because that takes away a factor of 2 when you take the derivatives. But for linear regression, ordinary least squares, it doesn't matter. So the function to look at then is a sum from I equal 0 up to n minus 1. And then it's yi minus yi tilde squared. So this is a function which we're going to look at now. And then we want to calculate the derivative of that one. So if you now think of the model which we have put in, you can now rewrite this as a 1 over n of I equals 0 to n minus 1. And then we have a y of I. And now it becomes easier to see how to calculate the derivatives. So next week in the exercises, we are going to, actually tomorrow, we're going to set this up in terms of a matrix vector product. And then in the exercises next week, we are going to analytically derive the derivatives of vectors and matrices with respect to the unknown parameters. So that is one of the exercises next week. But today we will, and tomorrow we will start just doing this term by term. So if you then write this out, what we have then, when we plug in the model here, is actually a sum from j equals 0 up to p minus 1. And then I have my x of I to the power of j times theta j, and then squared. So that means that when we write it out now, it's 1 over n, I equals 0 to n minus 1. And then we have a y of I minus, and then we have theta 0 minus theta 1 to the power of, multiplied with x, I to the power of 1. And this continues all the way up to theta of p minus 1 multiplied with x I to the power of p minus 1, like that. And then this is squared, like that. So we can write this in a much more compact way as a matrix times a vector, and you will see that immediately. And this is roughly where we will stop today, because the next thing which we need to do is, oh, let me just wait so people get time to write here. One of the drawbacks when you use a whiteboard is it's so easy to flip a page. When you have it on the blackboard, you have a better view of everything. Okay, so what we are going to do now is simply to calculate d of c of y of theta of d of theta j. And we want this to be 0. So we're going to get, if we have a second order polynomial, we will have 3 equations. If we have a 10th order polynomial, we have 10 equations, etc., etc. So this obviously becomes, these gradients become a vector of the parameters theta. So what we're going to end today is actually to rewrite this function C of y, sorry, in a more compact way. So we're going to write it like this. And then we write it like a y. So this is a vector minus the matrix x times theta. And this is a vector, and this is squared. Is this a notation which rings a bell? So this is a norm 2 of a vector. So keep in mind now that this object which you see here, this is a vector, and this is also a vector, right? Because it's a matrix which has dimensionality n times p, and which then is multiplied with a vector of dimensionality p. And that gives us a vector of length n. So these are just two vectors, and it's squared. So let me just remind you of this notation here, x squared. This is just this norm 2 of a vector. So if I take I equals 0 up to n minus 1, this is simply x of I squared. So when I put a number 2 here, up here, that simply means that this is the object square. So I can rewrite it in another way, which is also one of the ways you will see this in many, many textbooks. So the final way which I'm going to plug in here, and this is where we stop today. This is also like 1 over n, and then we have y minus x times theta vector transpose times y minus x times theta. That is equivalent with that expression which you have here. So these two expressions are the equivalent. Yeah. The summation. Oh, sorry. Thanks. Yeah, no, this was, sorry, this is a flip of pen here, thanks. I didn't do it on purpose, just to see that people are following, no. So if you see something which goes wrong or is wrong, just raise your hand. So tomorrow, we are going to look at the derivatives. And I just wanted to anticipate the result, which you're going to see. So the result, which we will derive tomorrow, is that theta, these unknown quantities, are going to be given by x transpose, inverse of that matrix, multiplied with x transpose, multiplied with a vector y. This is what we will get. It's an analytical expression in terms of a matrix product, inverse, times another matrix, times a vector. So x is known, y is known. So we have an expression for the parameters theta, where we learn the parameters by solving that equation. So this is what we will derive tomorrow. And then we're going to discuss a little bit back and forth, what it means and consequences, look at codes, etc., etc. So that's the schedule for tomorrow. So I will send you an email with small updates, etc., etc., and some small reading assignments. Questions? Things unclear? Too simple or whatever? Okay. So tomorrow we will have a more regular lecture, but next Tuesday we will treat this as a kind of a flipped classroom with questions and some lecturing and questions, etc., etc. Okay. Hey, good luck with this semester start, right? I'm just gonna switch off this one.